Hello, welcome to this short video on an introduction to NumPy in Python. In this video, I will discuss the basic features of NumPy, and then I will discuss how we can create arrays, which is the basic data type of NumPy, and then what are the possible basic functions that we can and operations that we can do with these arrays. My focus since is on scientific computing, so I will discuss those operations which are going to be needed for scientific computation. And then we will briefly discuss how we can access different elements and parts of the arrays. At the end, I will briefly discuss a couple of functions that we can do with these arrays that are equivalent to linear algebra, just like in MATLAB. So the basic data type in NumPy is this array called NumPy array. You can create multi-dimensional arrays using this function and then work with these. The data type in these arrays can also be specified, like we can have integer arrays, float arrays, complex numbers arrays, and even arrays that have Boolean data, for example, true and false. This data structure can be used to work with multidimensional functions in scientific computing and matrices without the need for loops, because we can do operations on the whole array with the single commands. Um, therefore, this provides functionalities similar to MATLAB for handling matrices, but the arrays in Python are more flexible and there is more functionality available than MATLAB. For physicists, that this talk is mainly focused on, the most common use of NumPy is creation of arrays and especially the creation of matrices and linear algebra, but also its use for working with the one-dimensional functions. Several packages like Pandas, which is mainly for data science, and SciPy, which has advanced features for scientific computations. All of these packages are built using NumPy array. So this introduction to NumPy array will also help you uh, get better idea of Pandas and SciPy for data science and scientific computation. Of course, this introduction is very brief and only touches the basic features and functions. And if you are interested in finding the full range of functionality and tricks and tips for handling NumPy array, please visit numpy.org or scipy.org to see the full functionality. Or you can also see right inside, let's say, a spider by using help. Okay, so we can create arrays in several ways of various shapes, dimensions, and sizes. For example, let's begin by importing NumPy package as np, and I can create a one-dimensional array simply by writing np.array and this one, two, three. These are three elements of this one-dimensional array. Or I can create, let's say, this array. This though looks like a 2D array, but it's not. It's actually a one-dimensional array. Its first element is this array 1, 2, and its second element is also an array of three elements 1, 2, minus 1. This is not two-dimensional array because the number of elements here and number of elements here are not the same. When the number of elements are not the same in two dimension, then NumPy treats it as a list. Similarly, if you see here this array C, it's a two-dimensional array, but it's like this. So in the first dimension, we have this element 1, 2, and 1, and then in the second row we have this element. This is 1, 1, and this is 0, 0, another element. So you see we have this two-dimensional array, but the elements themselves can be arrays or list. We can also create arrays. Let's say if we want to create an array of all zeros, which is two-dimensional. So in the first dimension there are three elements. In the second dimension there are four elements. So this will create a 3 by 4 uh, array of zeros. Similarly, if we want to create an array of ones, I can specify it like this. This is a 2 by 2 array of ones. And optionally, we can select the data type. For example, here it is complex, here it is int 32. You can put NP or not. This can work either way. And just one point which I was discussing here, it's always important to remember that if number of elements in the same dimension are different in different elements, it is treated as a list. So let me, for example, show you quickly by going to Spider. Suppose I have let me clear it, import numpy as np, and if I create an array np.array, so this is, let's say, 1 2 3. So let's create a 2D array. So 1 2 3 like this. So let's see what A is. You see, this is a nice two-dimensional array with three elements in each row and with two rows. But if I have, let's say, an array which has different number of elements here, for example, here there's only 1 2 and 1 2 3. So let's see what A is now. So now A is an array which has first element as list and the second element is also a list. So this is what I was talking about, that if the number of elements are different, then it's treated as a list. So let's go back to this presentation. We'll switch back to a pointer as a laser pointer. Okay. So this is how we can create basic arrays. I would urge you to uh, do these two practice commands. Okay, so let's now discuss how we can create one-dimensional arrays, because this is actually one of the common arrays that we encounter in data science and scientific computing, and there are several ways of creating these one-dimensional arrays. We can have what we called NP range, where we can give the starting point, the stopping point, and the interval. For example, here I'm trying to create this one-dimensional array, which starts from minus 0.9, ends at 1.3 with a difference of 0.25. So it starts at minus 0.9 and keep going until I'm either equal to 1.3 or higher than 1.3. So it creates this 1D array. We can also create it using this function called linspace. So with this linspace, I specify the total number of points in the array, which has the starting and an ending point. So here I specify 4 points. It's compute the interval automatically, and it starts from the initial point and it ends at the final point. There are another way of computing the 1D array if you are only interested in integers, that is through range. We know that range creates a list of number uh, uh, from starting point to an ending point with an interval which is specified here. For example, the interval is 2. And then if we put this thing in np.array, it's like casting the type of this list, one-dimensional list, into a one-dimensional array. So it recasts this range list, the list created by this range function, into an array. For example, this also creates an array of integers from 0 to 6, because we didn't specify any starting point, and if we don't, it's 0, and the interval by default is 1. So this is how we can create 1D arrays in Python. Let's now see the basic properties of these arrays. So we can check or we can specify the dimensions ourselves. And in Python, it's actually referred to as access when we are specifying, or you can say the language in which we refer to these dimensions is called access. So we say that if like it's three-dimensional array, it has three axes, and its shape is defined as a number of elements along each axis, uh, and its size gives us the total number of elements in the array. For example, we can see it from an example here. If we have this array, so you see it has it's a matrix where there are two columns and three rows. So its size is 6 because 6 is the total number of elements. Its shape is 3 2 because it has three rows. So what you can say, in along the first dimension, it has three elements. So this is 3. Along the second dimension, which is the column dimension here, it has two elements because there's one column here, the second column, so this is 2. Even though its shape is 3 by 2, but it's still a two-dimensional array because we are specifying elements along two dimension. You can imagine one dimension here and the other dimension here. And this ndim gives us the dimension. All matrices are two-dimensional, even though their shapes would be different because we will have different elements along different axes. And the size is just the total number of elements. It compute all the elements in it. And just to emphasize the previous point again, the size thing is a bit tricky if you have unequal elements in different dimensions. For example, if we look at this list, so this is a one-dimensional list because uh, if we look at it, it doesn't have the same number of elements here and here. So it's treated as 1D array. So this is the first element 1, 2, it's a list. The second element is a list with only one element. The third element is another list with two elements in it. So as you can see from the printed version here, it's a 1D array. Of course, its elements are lists themselves. So therefore, if I check its size, I will get 3 because there are three elements: one, two, three. The element themselves are lists, but that's another point. Now its shape, it's a one-dimensional array because it's only one-dimensional. Along the second dimension, there's nothing. So 1D array is specified as 3 comma, and its shape is 3 comma because there's nothing on the other side, and its dimension is 1. Okay, so this is how we can check basic features of these NP arrays. And let's now see the multiplication, because this is one of the important thing that we will be doing with these arrays, is that we would be multiplying different arrays with themselves or an array with a scalar number. So uh, one way of multiplying is through the star operator. So what does the star do? You can also call it a scalar multiplication or element wise multiplication. It actually operates element wise. For example, this 2 star A will multiply 2 with each element of this array. For example, 2 ones are 2, 2 twos are 4, 2 threes are 6, 2 fours are 8. And if I have this array, let's say another array B, and if I multiply this A with B through star, it simply multiplies the corresponding elements. So 1, 2, 1 multiplies with -1, we get -1, 2 multiplies with 0, we get 0, 3 multiplies with 1, we get 3, 4 multiplies with 2, and we get 8. So when you multiply two arrays through star, you will get an error if A and B are of different size and have different dimension, because then it won't be able to work. With one exception that I will discuss shortly. So for this A star B to work, the dimension and sizes have to be the same. If they're different, you'll get an error message. Now here again, there's a you have to remember one thing. For example, if you look at this array C, this is a 1D array and it has 4 elements. but all elements are lists themselves. For example, this is a list, this is a list, this is a list, this is a list. Now when I multiply the C with A, this is what I'm going to get. So this 1 by 2 list is going to be multiplied with 1. So I get 1 by 2 back. This 3 is going to be, this list is going to be multiplied with 2. Now, if you recall, when we multiply list with a number, we actually prepare copies of that list by that many times. So 2 into this list 3 is actually 3, 3, not 6. So similarly, when this 0, 0, 0 list multiplies with 3, we get 3 copies of this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have these 9 zeros in the third element. Now when this 2 gets multiplied with 4, so this is not the multiplication of 2 with 4, but essentially the multiplication of this list with 4. So we get 4 copies of 2, 2, 2, 2, 2. So this is an important point to remember. If we have an array of lists, then multiplication will work totally differently than the multiplication that is working between A and B. As an experiment, let's just see what happens if we multiply this array of list with C, because this list C, sorry, let's see how this C multiplies with list B, because B has this -1 and 0. So when this 1 to list multiplies with -1, we get an empty list, because this multiplication is not defined. And when similarly this list 3 multiplies with 0, it means we need 0 copies of 3, so we get an empty list. So the rest is obvious. This 0, 0, 0 list multiplies with 1, so we get 1 copy. When this 2 gets multiplied with 2, we get 2 copies of 2. So this is how this star operator work in general, that when dimensions are same, the corresponding elements are multiplied. And when multiplication is happening, we have to remember that when list is multiplied with a number, we get that many copies of the list. Okay, so let's now go to this one exception, that this product happens between two arrays of same size, except when one of the array is one dimensional. For example, if you look at this array AT, this is one dimensional. So it's a column matrix. It's 2 and 3. And if you look at this list C, this is also one dimensional, but it's a row matrix. So -1, 1, -2. And if you look at A is a two-dimensional array. So 1, 2, 3, 4, 4, 4. And now if I can multiply A star C. So in this case, you see A and C are of different dimension. This is one dimensional, this is two dimensional. But this product is still defined. And this happens in this way, that this row matrix multiplies with each row independently. So this -1 multiplies with 1, we get -1. This 1 multiplies with 2, we get 2. This -2 multiplies with 3, we get -6. Then the same thing happens. This row gets multiplied with the second row, and we get -4, 4, -8. Similarly, if we want to see this AT's multiplication with A, so now this is a column vector 2, 3. So what happened? This 2 gets multiplied with this row, and this 3 gets multiplied with this row. So we get 2, 4, 6, because 2 into 2, 2 into 2, 2 into 3, and 12, 12, 12 for the second row. And another important thing to note is this order is not important. This A star C and C star A is the same thing. So don't think of this as a matrix multiplication. This is still an element-wise multiplication, but Python has provided this flexibility that when you have one of the multiplying array is one dimensional and the other array is anything, it could be two-dimensional, three-dimensional, four-dimensional, and provided that the number of elements along one dimension matches the number of elements along each of each of the dimensions in the other multi-dimensional array, the product is still defined. That array gets multiplied with each of the row or each of the column in the other array. Okay, so that's why this product is much more flexible than the scalar product, let's say, available in MATLAB, or we can generally think of. Okay, let's now get to the most important operations with respect to the scientific computing. Because NumPy provides us a lot of functions. They're called universal functions that we can do with arrays. For example, if I have this 1D array X, and I can take square of each of its element by simply taking x square. It will give me square of it will give me an array that has square of elements each of its element. For example, I can create this x array using a range from -3 to 0.9. It's here, and I can find exponential of each element by writing np.exp of x. So this is an array whose each element is the exponential of the corresponding array in x here. The other functions available, like we can do sine, cosine, tangent, exponential, log, etc. And the other important thing is that we can also do logical operations with these arrays. And if you want to see what are the other functions available, just go to Spider and type help numpy, and you will see the whole list. As I was saying, there are many other universal functions available. For example, we can do logical operations. For example, this is an array B of these numbers, and here I'm checking if B is equal to 0. So if B is equal to, I'm comparing each element of B with 0, and I'm getting a Boolean array in which each element, either true or false, which depends on comparison of each element with 0. Since none of this is 0, we get false everywhere. And this is another array which is true, which has element as true if the number is greater than 2, and is false if number is not greater than 2. For example, this 1 is not greater than 2, 2 is not greater than 2, so I get false, false. But for 3, 4, I get true, true, and then true, true all the way here. Similarly, we have other functions available. For example, if I look at this array, we can compute average of all of its elements by simply writing average. All what it does, that it adds up all the elements and then divide by the number of elements. You can actually do the same thing with another function called mean. So this is a syntactic sugar in Python, that you can do two things, one thing with two functions. Similarly, we can find the maximum element of this array by writing this max of a, or the minimum element, or we can sum all the elements over here by using sum. We can find transpose, which is going to be useful in linear algebra. And of course, as I was saying, you can find all the available function using help numpy. Let me just take a look what you get by typing help numpy. So let's say help numpy. Okay, so you see here I get the doc string of this numpy package. So I can't see all, but uh, you can see, for example, the functions available here. Uh, so it's telling us that we can stack arrays like this, and the universal function, for example, data types are given here. We can have int32, we can have float64 data types. So you can create lists of zeros and arrays of zeros with this function zeros. So these are all the numbers that are available here. We can specify infinity with INF uh, and all other options here. Okay, so these are universal functions that are available. For example, we have arc cosine, we have arc cosine hyperbolic, we have arc sine, we have arc sine hyperbolic, bitwise not, bitwise and, or these logical operations. We have these functions: ceiling, conjugate, cos hyperbolic. So you see there's a whole range of functions that are available. For example, log, log 1p, log 2, log 10, logical not, etc. So this help numpy tells us everything that is available in this package. So let's go back to our presentation here. Okay, let me shift to laser pointer again. Okay. All right. So I would like you to stop here and do this small activity. What you should do, create a 1D array, let's call it X, from 10 to 65 with 1000 points in it, and then compute this another 1D array, which is actually this function, and then create another array such that it has 1 at its place. Each element is either 1 or 0, and it is 1 if if element of this array y are greater than minus 0.5, and it is 0 if it is either equal or less than minus 0.5. And once you have this new array, uh, we should actually had called it something else. So not y, actually, let's call it, make another 1D array. Let me call it z, and then I want you to plot this new array z as a function of x. And in doing all of this, you are not allowed to use any loop for the above. And just remember, when you have to plot, you will have to use another package, for example, matplotlib, or you can use pyplot, because plotting is not available in numpy except the histogram, which we are not doing here. So I want you to do this plot. Let me use the laser pointer here. Okay, so do this plot of this array z as a function of x. So the idea is this, that you get to work with the 1D arrays and see how we can do a lot of things without using loops. Okay, let's now see how we can access different elements of arrays. For example, we have an array A. This is a two-dimensional array. It's actually a sort of a matrix, 3 by 2. So we can access its first element by writing A0. And you see the first element is this first row 1, 2. Because when we specify uh, only one axis, if only one axis provided, it is taken to be the first. So what happens that if you only supply one index, it takes this as the index of the first axis. So the first axis here is this, in which this is the first element, this is the second element, this is the third element. So a of 0 is this first element, a of 2 is this last element. So if you only specify one index, it is taken to be as the index of the first axis. So this is how we can access uh, the the elements on the first axis. But if you want to specify one of the element exactly, for example, this 1 1, specify the second element and the second element on both axes. Remember, the index starts at 0, so this 1 means the second element along first axis, and this 1 means second element along the second axis. So the second element, the second element along first and second element along second axis is the 7, because you can just look right here. So this is dimension 1. This is the this is, sorry, axis 1. This is second axis. So along axis 1, we have this second element, because this is 0 index, this is 1 index, this is 2 index along first axis. In the second axis, this is the first index, the 0 index, this is the 1 index. So the 1 1 element is 7. Similarly, we can select a bunch of elements, which is called slicing in Python. So we can slice through any axis. For example, over here, I'm slicing through the first axis from 0 to 2, which actually mean 0 to 1, because I hope you still remember that in when we specify the index like this, it goes from 0 to whatever is specified here minus 1. So 0 and 1 element in first axis, which is uh, and in the second dimension we have 0. So this is in the second 0 selects this one, and 0 to 2 selects 1 and 6. So that's why you see 1 and 6 printed over here. So this is how we can index and slice different parts of an array. And just like lists and sets that we saw earlier in Python, we can also use these arrays to, iterate in loops. For example, if I have something like for some integer, for some variable m in A, where this A is this array A, then m will first take this value, then m will take this value, then m will take this value if you're using m in a loop. Because this is consistent with what I was saying here, that if you only specify one index, that index is the index of the first axis. So it iterates over elements along first axis if you specify array in a loop like this for m in A. Okay, so this is how we can access different elements in arrays. And let's now see what we can do with matrices in NumPy, which is actually very easy and very useful for computations in science. So, for example, here I'm creating a two-dimensional array using this np.i. This I is actually identity matrix of 4 by 4 size, and I'm combining this one with an array of ones, which is also has a size 4 by 4, and I'm taking this array of 1 to have a data type complex. So when I subtract from identity this array of 1, of course I get 0, 0, 0, 0 on diagonal, and minus 1 everywhere else. Okay. Similarly, I can create a 1D array, let's say B, which goes from 4 to 7 with an interval of 1. So I have this 1D array of 4 elements, 4, 5, 6, 7. And now we can see that the matrix product in NumPy specified this at operator. So if I write A at B, this is actually telling NumPy to do the matrix multiplication of A and B. So when I multiply A and B, I get this 1D array, which is actually the matrix multiplication of A and B. And as you can see, even though when we learn matrices, we know that if there's a product of a square matrix and a column matrix, AB, we can do the product in reverse. But if we specify the reverse product in Python, we still get the same answer, because what Python does, it turns this it adjusts the dimensions of B and A by taking the transpose of this 1D array, so that we end up getting this same result. So by using this at operator, we can do this matrix product. Okay, we have other options available in linear algebra. For example, we can find trace. Trace is nothing but the sum of all diagonal entries. So since here all elements are 0, I get 0 answer. So this j is there because the data type is complex. Now, if you we can also solve a system of linear equations. For example, if we have a system Ax is equal to B, where A is the coefficient matrix and B is the column matrix on the right side, and X is our unknown, we can find those X by simply this from the simple command lin algebra dot solve AB. So this A is the coefficient matrix and B is the column matrix, and you see it gives us this solution right away. So we can find solution of system of linear equations using numpy very quickly by using this command. And if you want to find eigenvalues and eigenvectors of a square matrix, we can use this command eig. And when we do and supply a square matrix here, what we get are two arrays. The first arrays is actually the arrays of eigenvalues. So this is my first eigenvalue of A, this is second eigenvalue of A minus 3. This is the third eigenvalue, and this is the fourth eigenvalue. And then I have another array which actually has the eigenvectors. So the first eigenvector, this 0.86, 0.5 minus 0, minus 0.54, minus this. So this is this is one number. So 1, 2, 3, 4. So this is a 4 by 1 matrix, row matrix. So this first row is actually the eigenvector corresponding to the first eigenvalue. The second element of this array is the eigenvector corresponding to the second eigenvalue, and this third array, which is part of this array, is the eigenvector corresponding to this eigenvalue, and the last one corresponds to this eigenvalue. So using numpy, we can do a lot of operations that we do with linear algebra. For example, transpose, eigenvalues, numerical solution of system of linear equation, and so on. You can see the other available options at numpy.org. Okay, so now I want you to do another quick activity again. So here I have a Hamiltonian of ammonia molecule in an external electric field, where this epsilon 0 is the energy, epsilon 0 and A specifies the energy of the molecule, of this two-state molecule in the absence of electric field. Electric field is E here. And what I want you to do is find the eigenvalues of this matrix. So this will have two eigenvalues for a fixed epsilon and A values. So this is 0, this is 1 electron volt. But for E, I want you to vary E from minus 5 to 5 volts per nanometer. And let's say you can take, I don't know, maybe 1000 points from minus 5 to 5. And for each value of E, I want you to find both of the eigenvalues, which are actually the eigenenergies of the Hamiltonian operator corresponding to this electric field E. And then prepare two lists. One list that will have all the eigenvalue, the first eigenvalue corresponding to each value of electric field, and the second list will have all the second eigenvalues corresponding to the same values of electric field, and then plot those eigenvalues. Um, you What you can do is maybe implement a loop over E, where E goes from minus 5 to 5 with some very small interval, and then at each point, at each iteration, you use this np.linalg.eig function for computing eigenvalues, and then pick those eigenvalues out of the arrays that are given by this function, and then at the end plot them. Okay, so with this, I would like to end this short introduction to NumPy, and I hope that this was helpful in introducing you to the basic features of NumPy. Thank you.